Welcome back, everybody. Somebody found a typo here that I fixed, and I will re-upload. Is the one should be here and not here. So I moved it over, and now it should be doing the correct computation. That's actually, in fact, the same thing as the U and Y, the U or Y computation that we had earlier. All right. So let's come back to our system, where we saw the definition of precision. Who already saw precision before? I assume that's probably not new to all of you, right? Raise your hand. Okay, in machine learning, was it in machine learning? Yes, so there, all right. So maybe you know what recall is. Can anybody tell me what the recall is? Yes? False positive or false negatives? Let me help you here. So that would be the false. Exactly, so the relevant. So let me show it to you. This one, so this is now the full grid. And so what you are describing, and you are correct, this is technically among the results that are relevant. So what the user actually is looking for. What is the ratio that we actually return? So that is true positives divided by true positives plus false negatives, right? So if you do it with the false positives, that's the precision, and then if you do it with the false negatives, that's the recall, right? So you're correct about the definition, first definition you gave. All right, so this is the recall. So it's the true positives, that part right here, divided by everything over there. All right, who is with me? All right, then who can tell me what recall this is? Everybody at the same time. Okay, 1, 2, 3. 50% exactly. This is 50%, A divided by 16. This is 100% because now everything that there was to return, we returned it. We didn't forget anything. Now this is 0, that's a catastrophe, right? Everything that was relevant, we didn't return any of that. And here it's 2/3, 67%, right? So that would be 8 divided by 12, all right? So now there is something that I never, ever managed to remember. I kind of gave up in the end. It's the type 1, type 2. I never remember if it's here or there. But I think here I checked, so that should be type 1 error is false positives, and type 2 error is false negatives, right? So this here, this way of looking at things, exists in many, many different areas. Information retrieval is one. Another one is machine learning. For example, when you want to classify as a yes/no, then typically that's also falling under this kind of classification. And this is why the notion of precision and recall is just absolutely everywhere, as well as the notion of type 1 error, type 2 error, false positive, false negative. Who is with me? Yes, okay, very good. This is a system with very high precision. 80%, right? 80%, high precision. This is a system with high recall. What is the recall here? Roughly 80, 89% or something, I think, right? 8 divided by 9. All right, so you see, high precision, high recall, and now, as you might have guessed, the tricky part is to get both at the same time. And in fact, it's close to impossible to actually get both perfect precision and perfect recall. So in the end, it's going to be a compromise. mostly based on what are the consequences of false positives and false negatives. And that depends on the context. In some contexts, false negatives are really, really bad and false positives are kind of okay. In some other contexts, it's the other way around. Now, in the context of a search engine, you probably care a lot about the precision because you want what you see in the ranking to be to actually be helpful. On the other hand, you also want, if you're looking for something specific, you would like to see it in the results. So again, that depends, right? So it's a compromise to make between the two. Okay, I'm closing that. We'll come back in a couple of weeks to this, where I will give you other definitions, like accuracy, which should be avoided. Probably they told you that in machine learning too. Specificity, the ROC curve, and so on, the 11-point interpolation. So I'll tell you a lot about what we can do with this kind of measurements of quality of a system. Okay, but let's go back to our matrices. These beautiful matrices with Booleans inside. It's actually not so great, right? Because the example that I gave you has 10 documents and 6 terms, right? But that's not what's going to happen in reality. I mean, I don't know of any library that just has 10 books with 6 words, 6 different words in there, right? So in reality, the number of terms that you might find, I don't know, let's take the library of ETH. Maybe we're going to find 500,000 distinct terms, right? If we do some cleanup and we ignore a few things, but let's say 500,000 terms. Sounds reasonable, right? It's so typically in a language, there's maybe a 5-digit number of words. English a bit more than in French, for example, but we're in the 5-digit range. And if you add all of the names of countries and people and all kinds of compound expressions and brands and so on that you can imagine, then you can easily arrive in the six digits. Okay, so that's a pretty tall matrix, right? Now the documents. So let's say maybe a big library of a good university might have a million books, right? So I told you the Library of Congress, I think there are hundreds million, I think, but typically there's many libraries that have 1 million documents. Does anybody start seeing the problem here? That's a big matrix. We have to store in there 500 billion Booleans. So that's a big problem. What scares me more is that it actually fits on a laptop today. Because now we can have hard drives big enough. So technically, if you're crazy enough to do it, you could actually do it and implement it in that way. But as you might have guessed, maybe this is not the best way of doing that. Okay, now, how many zeros do you think that there are in there? Very few, half of that, very many. Who thinks it's half-half? Who thinks there would be very few zeros? Some of you. Who thinks there would be very many zeros? Most of you. And indeed, most of you think it's sparse. Sparse is the name for that. We don't have a lot of ones. So it's mostly empty, right? Because typically, if you look at a document, let's say we have 1,000 different terms per document. Of course, it depends how big you take the documents, right? Is it a web page? Is it a book? But just to give you some orders of magnitudes, you might have 1,000 terms in there that are set to 1. And you have to realize that it means that there are 499,000 that are set to 0, right? So that's actually a lot of zeros if you look at that. So we are going to have 1 billion ones. So taking a very, very rough estimate, there's going to be 1 billion ones in there and 499 billion zeros. And when you have some sort of skew like that, it starts sounding like it's not optimally stored. You can do better than that and store it in a more optimal way, because maybe we can just not even store the zeros in a way. So is there any way that we could just design a structure where we only store the ones? Of course. And that's what people did. And it's 99.8% empty. It's space inefficient. I think I have a question for you, but oh, that's the question. And now I click to the clicker. So that's my question to you. Can we do it in a better way? And now comes the clicker question. All right, that's. So how do we solve this sparsity issue that we have 99% of 0? So do you rent a cluster of machines on Amazon and hope that finance and controlling doesn't go after you? Or do you list only the terms used by each document rather than mark all terms with zeros and ones? Or do you list only the documents containing each term rather than mark all documents with zeros and ones? Or only Google knows that you have an NDA you can't tell us? And I hope I got that right, because that's typically the sort of questions when my brain easily swaps between the two similar answers. Let us see what you say. We have a majority, and the majority is indeed correct. And that's what I meant. I'm sure I meant. So the majority is no, the majority is incorrect. I was correct. This is correct. Took me a while. This is correct. This is the correct answer. And so the 13 of you who got this right, congratulations. This is the correct answer. Why this answer and not the second one that look incredibly alike? Put yourself in the shoes of the user. The user is interested in giving you terms, and they want the documents that go with the terms. So you should design your structure in such a way that the entry point of the structure are the terms. And then for the terms, you get the documents. So that's why we list the documents containing each term. So for each term, you list the documents, and we do it in that way. If we did it the second way, that's also mathematically correct. You can also build a structure that would list the terms that they are in each document, but basically that's not very useful, because the entry point here would be the documents. The second answer would basically be that you basically take each book and put it through some sort of mixer that turns it into a set of terms, right? And there's no way you can use that to know where to find what you're looking for. Who agrees? All right, so we need the entry points to be the terms. That is the reason, the reason why answer 3 and not answer 2, that's called inverted. We take the inverted version of what the original collection was. The original collection has documents that contain terms. We invert the whole thing and take the documents that contain the documents that contain the terms, right? The other way around. So we will call that a standard inverted index. And now you will remember the reason for inverted is that we take answer 3, even though it's less intuitive. All right, so let me go back. Five, that should be now. Probably this one. Exactly. So if you start with the matrix view, which we will not implement, but just that was our starting point, I put these green ticks everywhere there's a 1, and I didn't put them where there's a 0. Answer number 2 of the quiz would have been to look at it in this way. You look at the columns. For every column, you list the terms. That would have been answer 2 of the quiz, the one that is not very useful in practice. Answer number 3 is doing it with the rows. For every term, you have a list, an actual linked list of documents. And here, for U, you have a linked list. For V, you have a linked list. That is answer 3. And so if I actually do it, for example, here the ticks are at 1, 4, 9, 10. So I build the list 1, 4, 9, 10. These are actual integers. because that's called the document ID. I'm giving labels to the documents. This is document 1, this is document 2, this is document 3. So I'm assigning them integers, doesn't matter in which order. And now I have a list of integers. So T is associated with this list of integers, U is associated with this list, V is associated with this list, W with this one, and so on. So now, if I clean this a little bit up, this is what I end up with. Who agrees? This is the same thing? Very good. It has exactly the same information. And again, this is a standard inverted index or an inverted file because we do it the other way around of what would be the intuition. We tend to think of documents containing terms. We completely turn that upside down and instead have the terms here and then list the IDs of the documents that contain the terms. For example, you can see that term T is contained in documents 1, 4, 9, and 10, or that document 1 contains term T and contains term X. Who is with me? Very good. Take a good snapshot of that in your brain. This is going to be the entire semester following us. It's called the standard inverted index. We'll modify it, we'll add stuff, to tweak it, but this is the one most important structure that underlies an information retrieval system, at least before LLMs, pre-LLMs, right? So now a bit of terminology so that I'm trying to get the names precise. These yellow boxes here, these are called the terms. All of them together, that's called a dictionary. We will see later in another lecture that there is a data structure to organize the terms, but I'm not talking about that yet, right? But we have a dictionary of terms. Then we have the documents. So this is one document, this is document 4. And you notice document 4 will appear every time that it contains a term, right? So here it appears 3 times because it contains 3 terms. But this is the one and same document, that's document 4. Now, if I look at only one of these, not all the 4s, but just one of the 4s, then that's called a posting. So that might be a new word. Whoever heard that word before, posting? Nobody, right? So this is called a posting. What is a posting mathematically? It's a pair of a document and a term, such that the document contains the term. So this is the pair X4. And the presence of that pair, X4, means that document 4 contains term X. And now you might ask, if a posting is a pair, then what is X doing? We are missing X, right? We just have 4. But this is just an optimization. If you go to the left, this is where X is. And X is shared by all the postings on the same row. So this is, in fact, here it's X1, X3, X4, X7. These are the postings. But since everybody on that row has anyway the same first item in the pair, then we don't bother to write X again here. So this is why we just write the integers. But what's important is that if you look at just one of these integers, as opposed to all of the 4s, just one of them, then that's not a document, that's a posting. Right? That's the posting X4. For whom is that clear? Right. And a posting corresponds to one cell with a 1 in the matrix view. Now, obviously, if this is a posting, then this is called a postings list. Right? So postings list is something you are going to hear a lot in the lecture because we are going to optimize them in the way we store them and so on. So that's called a postings list. All of these together, that's referred to as the postings. So the dictionary and the postings, these 2 parts. All right. And this together is called the index or the standard inverted index. Right? Are you okay with the terminology? So again, we have term, dictionary, document, posting, postings list, postings, and index. Right. I'm trying to be very careful with the terminology because as we keep introducing new words, we'll also talk about tokens, positional tokens, and so on, and it keeps getting more complicated. So I'm really trying my best to keep the terminology consistent, to not lose you. By the way, there is one little more thing that we add to the standard inverted index to make it really standard. That's the purple boxes that I put in there. These are called the document frequencies. We'll also spend an entire week on them. Can anybody guess what there is in there? What do the integers correspond to? Pretty sure somebody will guess. Yes? Exactly, the number of documents containing the term, which is the length of the list, basically. So you see the first list has 4 postings, so that's a 4. The second list has 3 postings, 1, 2, 3. This has 5, 1, 4, 3. Okay. So we call them the document frequencies. So a document frequency is associated with a term, and that tells you how many documents contain that term. A very high document frequency means that it's a term that you see everywhere, like and, a, the, is, be, that kind of words. And very low document frequencies are terms that you barely see anywhere, right? So like supercalifragilisticexpialidocious kind of terms that have a very low document frequency. All right, I marked the most frequent term in here. That's probably a word like to be, and W is probably a very rare word. All right, then comes how do we build that index, right? Because here I directly gave you that index, but we need to build it. So I'm going to go on a high level through how we take a collection and build the list. So I'm taking an example with just 4 documents. It's actually in the book, the information retrieval book. And the documents are very short because, again, that's to make it fit on slides, right? In reality, you would have maybe 1 million documents and thousands words per document. All right, so now there is a first thing that you need to do when you take these documents. You need to tokenize them. Tokenization can be very complex. Today, I'm going to oversimplify things by just taking the spaces and dropping the punctuation, right? So I'm taking the spaces as the tokenization. You already saw it's not that easy. ETH, Zurich, Unterwalden, Nibdenwald, and so on. Not that easy. Let's just take the spaces. Let's not overcomplicate things, and we'll talk about this later, right? So if I tokenize, then this is what I get based on the spaces. Then there is a second step that I'm also oversimplifying today, which is some kind of linguistic pre-processing. I'll just get rid of the punctuation to simplify things. Again, I'll tell you more about this and why it's actually much more complex than it seems. But I just got rid of, there was an uppercase to that. I kept the uppercase for the proper nouns. But yeah, just dropping the punctuation and taking the lowercase. All right? So now I have what are called tokens, because I tokenized. So now I'm going to reorganize these tokens. So I basically just take the transpose of that, right? Think the transpose of a matrix. I'm just organizing them vertically instead of horizontally, right? And I'm going to associate the integer of the document. So that's document 1, 2, 3, and 4. So 1, 2, 3, 4. So you see, now I have pairs here, a term and a document. Do you remember what they are called? Starts with P? Postings, exactly. This is a posting. You see, we start to see the things emerge from here. So this is a posting. Now, what do? I sort everything by term. So I just use a sorting algorithm, n log n, and reorganize that in this way. And now I'm going to take those that are similar and merge. So I have here, for example, these 3 that are together, and I'm just merging them. That's the trick that I told you earlier, that you don't repeat the document multiple times. You just group them, all of them, the postings with the same term here, and then you only keep the document ID in here. Do you see we're almost there, right? And now I just nicely add the linked list structure in there. And I didn't do it as fancy as the previous slide, but now we are there. And I'm adding the document frequencies. You see here there's just 1, here there's 3, and just 1 on the others. Who is with me? Who agrees this is our standard inverted index? That's it. That's the structure we were looking for the documents. So the lessons here that, again, you should remember, I oversimplified tokenization and linguistic preprocessing for today. It's much more complex in reality. But if you do that, then the algorithm for building this is relatively straightforward, right? You just reorganize them, adds the document IDs, sort, group, and then adds the structure. Okay, so there we go. And then once we have this, we can start, that's a standard inverted index, we can execute queries. Let's say query hour. How do I get the results for hour? Well, I'm looking for it. It's right here. And I'm going to return documents 1, 2, and 3. Right? It's as easy as with the matrix, except that now it's more efficient because we have this linked list. Right? Okay. So these are the documents, and typically one way that systems can display them, you've seen that, is with highlighting, right? You see the snippets of the text, and you highlight, I put it in bold in here, the words that you were looking for. Now, our end com here, I need to spot the two of them, and what do I need to do with the postings lists? I need to basically find the documents that are in both of them, because that's an end, right? So I need to return those that are in both, which are documents 1 and 3, exactly. These are the results. And we take, in fact, the intersection of these two lists, these two postings lists. And I get these two results very nicely. And now an OR, our OR, this, and I take these two, I found them. And I basically take now not the intersection, but the union, exactly. I take the union of the two, and oh, I get everything, actually. I get all 4 documents now. Okay, so this is it. Now, the intersection algorithm, we did it here because we're human beings and it was small enough. But what do you think the complexity is going to be of that algorithm, the intersection algorithm? Algorithmic complexity in the size of the number of postings. Who thinks it's exponential? Quadratic? N log n? Linear? Ah, a lot of linears, very good. Square root? Logarithmic? Okay. So indeed, it is linear. Does anybody want to do a PowerPoint karaoke and guide us through the linear implementation? Does anybody want to have fun? Otherwise, I can do it, right? But usually, so there are some volunteers. I'll click. You just need to talk. Does anybody want to do it? Yes? Okay, so let's give you a microphone. And I'll do the clicking. So you explain very detailed. You can also, I'll help you by clicking a little bit. So explain to us. You've done at least the PowerPoint karaokes, right? Is it still done now?
Yeah, it's on, but
okay.
We start at the start and then we check if these are the same, and in this case they are, so we pick it as part of the intersection and we advance. And here they're not the same, so then we have to advance the smaller one, the top one, further, and then still not the same, the smaller one is now the bottom, so we advance that, and then we are again in a situation where they are the same, so we pick it for the intersection and we advance both. And then again the smaller one we advance because it's not the same, and then again now the smaller one is the 6 in the bottom, 7 in the bottom, and once we reach 8 at the bottom, they are the same, so we pick it for the intersection and advance both. And yeah, we continue this, advance the top, the 9 to 10, advance it again to 12, and then advance the bottom one, and then 12, and then when we have reached the end of both posting lists, then we are done.
Exactly, we are done. Applause. So that's the way you compute the intersection of 2 posting lists in linear time. So as you can imagine, for the union, it works in the same way, except that you have more output. So you initialize the, does anybody want to do it? Okay, I'll do it then, okay. So we start with initialization of the 2 pointers. They are the same, we output it just once. Then we take the smallest one, which is 2, we output it and move it. Then the smallest one is 3, we output it and move the pointer. Now they're the same, so we output it and move both pointers. Now the smaller one is 5, we output it and move it. Now the smaller is 6, we output it and move it. Now the smaller is 7, we output it and move it. Then 8 and 8, that's the same. Move both pointers after outputting it. Now 9 is the smallest, we output it and move it. 10 is the smallest, we output it and move it. 11 is the smallest, we output it and move it. 12 duplicates, so we output it just once. And now we are at the end. That is the union. Who could implement that in Python? Yeah, very good. So that is how we can compute the intersection and the union of two posting lists with our standard inverted index. So you see, we are starting to get somewhere now, right? In terms of efficiency in space for the place it's going to occupy on disk, and the space is going to occupy, and in terms of computation, because now we have something that is linear in the number of in the length of the postings list. Now, another interesting question is what happens with more complicated queries. For example, let's start with AND. I have a query that is a conjunction of many, many different terms. And now you know that it's commutative, right? When you have an AND. So since it's commutative, we can freely decide about the order in which we are going to do these computations. So what order do you think I should take to be as efficient as possible in my algorithm? How should I order my terms here? Yes? So the rarest term first, and then by increasing size of the posting list. Exactly, that's exactly how you do it. So that, you know it. Why do you know the size of the posting list? Because it's right there, remember? That's the purple box. Oh, now I'm going to have to click in the other direction. That's the purple box here. So that we get for free. It's just a lookup. We search, of course, we still need to search the term. Probably you already guessed the memory structure for that, but I'll come back to that later. But then once we have the term, taking the document frequency is easy. Okay, all right. Coming back. That's the advantage that you see again, the intersection and the union, right? So now, because of these document frequencies, I know that Bibliopol is in 10 documents, Zurich in 100,000, and ETH in 10,000 documents, probably a lot of crypto documents as well in there. So indeed, you're absolutely right. I'm sorting these by increasing document frequency, which is the fancy name for the size of the posting list. And now I'm starting with Bibliopol and ETH, right? I'm computing the intersection. One further optimization that I can take is that instead of computing the intersection in a third location, I can modify them in place. That's one further optimization. So I can start with the rarest terms posting list, and then I can maintain the results in memory, right? So after I implement the modified intersection algorithm to modify in place with ETH, I already had a rather small list, right? But now it keeps getting even smaller. So you see how now we are really efficient because we really started with the smallest one in the first place, right? So it might take a bit longer to intersect with Zurich, but we'll see that there's tricks first to make it even faster. And second, that's just reading, right? There's barely anything to write because we are just going to remove some very few postings, all right? Who agrees with that, with this order? Okay, very good. Now, we might not only have ANDs, we might also have ORs. You might remember from your course on logic that you can always, when you have a Boolean formula that might be as complex as you want with AND and OR, and the not you can just squeeze into the variables, but AND or not, AND or, you can always write it in what is known as the conjunctive normal form. And its little sibling, the disjunctive normal form. Do you remember that? Right? So this here, if I'm correct, is called the conjunctive normal form. It's a bunch of ends, and inside the ends, you just have ORs, and that's it. It's just this two-layer structure. And when you do that, you use the conjunctive normal form. It's really nice because all you need to do is estimate the length of the ORs, and here you can very, very coarsely guesstimate as the sum, right? Of course, it's not the exact result, but you can basically just take the sum of the length, and that gives you an upper bound on the sides of the union. You agree, right? And so you can just sum them, and then you order the disjunctive statements with or smallest to greatest, and then you can run the computations, right? So you see the power of theory, you know, all your efforts that you put in the logic lecture, learning about this conjunctive normal form and so on, now it's actually having fruits, right? You can actually use that to make things faster. So I hope you see that there's many connections we are making here with other lectures, with linear algebra, with logic, with machine learning in a way, with the precision recall and so on. So yeah, that's one of the goals of this lecture, to see again some material we already know and connect it together. Now we are left with not. Not we haven't addressed yet. So in the conjunctive normal form, the not are just some of the atoms, right? You either have the variables or the negated variables, and then you can adapt the intersection algorithm or union algorithm by not actually computing the not. Because if you would compute a not, especially for a rare term, you would again get an absolutely huge posting list. So obviously you don't do that, right? And instead, when you have an end not, you just virtually walk through the list, but you just slightly modify the algorithm to just do the opposite of what it would otherwise do, right? And again, then you're space efficient in this way. So the exercise that you'll have, I think next week, it's next week, right? I think this one, it's next week. We always have an offset of 1 week so that you can digest the material. We'll give you that for free. Who has already seen that somewhere? Probably also in theory, very good, in theoretical computer science. That is called a context-free grammar in EBNF form. You won't have to implement it, that we give you. You will have the parser, it already gives you everything, but we will want you to implement the rest with you know, the standard inverted index, and we'll give you chunks of code, and then you need to complete in order to make it a complete system, right? So what you see here is just the grammar of our query language. Pretty small, pretty simple, but already very powerful. And in fact, the very early information retrieval systems, I would say in the 60s, this was more or less what it was based on, right? Boolean querying, right? And already very powerful because it already allows you to efficiently get the documents that contain them. Do you have any questions? Who enjoyed the lecture? Very good. All right. So I have just one question to ask you before you go. Oh yes, you can announce it, yes. Then I'll prepare, at the same time as you announce, I'll prepare the screen.
Today was a exercise session, but we'll do like a Python introduction, just a quick fresh up for those of you who have seen Python before, but for others who have never seen before Python. We'll give you a few notebooks to play around and make sure you're familiar with it for the exercises.
Thank you. So now I'm trying to load the screen. Yes, right here. So that's some remote control that I'm giving to you. You can accelerate me or slow me down. So basically, I will try at the end of most lectures, especially the toughest ones, to get a feeling for if I'm too slow, too fast, and so on. And then I adapt. If I'm too fast and everybody understands everything, I can accelerate. If I'm too slow and people are lost, if I'm too fast and people are lost, I slow down. And basically, the sweet spot, that means that it's al dente, is the 80 to 99%, if it means that the speed is about right. Now, of course, it's always going to be a bit heterogeneous, right? Not everybody will be in the same bucket. So if you understand everything, that's great. Then you can even take it to the next level, read really the book in depth and so on, make sure to understand every detail. I can even give you pointers if you're bored and you want to learn even more. If you are in the 50% or less than half, very happy to see there's nobody today, but of course, maybe later there will be. Well, don't worry, ask questions. The TA team is here, I'm here. You can also talk amongst yourselves. There is the element chat for this. It's win-win because the best way to learn is to teach. So if you ask somebody else to try to teach you, that will also strengthen their knowledge of the material. So do not hesitate to ask questions. So that's it. So thank you, everybody, for coming today. Enjoy the exercise session with the Python tutorial with the TAs, and I will see you next week at 10 a.m. right here. Thank you very much.